Okay, solenoids and toroids. These are where we take a loop of wire and we actually wrap it around to create a larger, more intense magnetic field. Now, if we have a single loop of wire, we've already come up with the expression for the magnetic field. If we take multiple loops, we're simply multiplying the effect of a single path of current. Instead of sending one loop of current around and then back, we send it around and around and around several times, and we get a multiplicative effect here and a much stronger magnetic field. The interesting thing is, with these solenoids, these cylindrically shaped coils of current, their magnetic field actually looks very much like the magnetic field we get from a bar magnet. And again, here's what the magnetic field will look like for the solenoid. At the center, it's nearly perpendicular to the coils of wire. As we get further and further away from it, these magnetic field lines tend to veer off. In using Ampere's law to solve for the magnetic field, we can again take a path. Instead of using a circular path like we did around a single wire, we're going to use a rectangular path here, and we are going to basically say that here the magnetic field, is integrated with the length is going to be equal to mu times I, or should say mu 0 times I. So now let's define something else. Small n is the number of loops divided by L. So that's going to be important because that's going to tell us how much actual current we have going through here. The more loops we have, the more current we have compared to the original current. So I is equal to N L I naught being the current that's going into the solenoid. We plug that into our original. We get L on both sides of the equation. We simplify this and we get that the magnetic field at the center of the solenoid is equal to mu 0 times N, the number of loops per unit length, times I, the actual current. So it's a really simple result that we get here, that the magnetic field depends on the density of how tightly wound the wires of current are, and I, the actual current itself. Again, more closely spaced, the solenoid turns, the more intense the magnetic field is going to be for a given current. We can also wrap this around itself, take a solenoid, and now wrap it around in a toroidal shape, and this is known as a toroid. And again, these structures are used for a variety of applications. Most of the time, because the magnetic field stays within the torus itself, these are used for inductors, and we'll talk about inductance in future chapters. But again, the magnetic field is greatest inside these coils, and we can actually, again, use Ampere's law to calculate that. We didn't do that here, but the magnetic field for a toroid goes by mu 0. N is the number of coils, I is the current, and of course R is the radius of the toroid.